The next two examples of solving rational equations are a little bit more complicated. They have a couple extra steps in there that you got to go through, but still the main idea, the main premise is you want to eliminate your fractions by multiplying through by your least common denominator. They're also making a point here, once again, make sure that you check your solutions because you can introduce extraneous solutions whenever you multiply both sides by a variable x. So the first step in this problem, whenever I approach rationals, I don't care if I'm trying to describe what the graph is going to look like, if I'm trying to solve them. The first thing that pops in my mind is I want to make sure that if I can factor these expressions, I need to factor them completely. And that's where this trinomial is going to factor into two binomials of x and x. Signs have to be plus and minus. The factors of 18 that are going to work are minus 6 and a positive 3. And what you're going to notice is that this x plus 3 factor is a common factor of x plus 3. The x minus 6 is a common factor with x minus 6. This is a fairly common occurrence in these rational equations, the way that they make them, so that some good things happen when you multiply through by the least common denominator. So first thing I'm going to identify the least common denominator. I got to make sure that each factor is represented at least once in my least common denominator. So if I represent the x plus 3 and x minus 6 once, what I get is an x plus 3 and an x minus 6 as a common denominator. So the least common denominator is our x plus 3 times our x minus 6. Our idea is to multiply through both sides of the equation by your least common denominator. So the 2x all over, x plus 3 will get multiplied by it. And also our 3 over x minus 6 will get multiplied by it. So that's taking the left side times our least common denominator. And I also want to take the right side times our least common denominator. So the x plus 3 and the x minus 6. I want to multiply it times our choice for least common denominator, which is x plus 3 times x minus 6. And if you want, you can put it over once so that you can see your fractions a little bit better. Sometimes it's nice to see numerators and denominators a little bit more clearly. So what you're going to need to do is you're going to need to distribute this product to the first term. And when you do so, the x plus 3 will cancel out with that x plus 3. So all that I'm going to have to multiply together is the 2x and the x minus 6. So it's going to be 2x times x minus 6. When I distribute to the second term inside of our binomial, this time the x minus 6 is going to cancel out with that x minus 6, and what we're multiplying together is the 3 and the x plus 3. So we have a plus sign, so we put plus 3 times x plus 3 equals. On the other side, it's not really a distributive property because we are not distributing over addition, we're just multiplying two fractions. And our two fractions have common factors in the numerator and denominator, so we just get a 27. So the whole purpose and intent of multiplying through by the least common denominator is to clear your fractions. We now have an equation that is void of fractions, and now we'll just distribute the rest of our terms out. So we have 2x squared minus 12x plus 3x plus 9 equals 27. Because it's a quadratic equation, our strategies that we've learned is to get one side equal to 0. So I'm going to collect like terms. I'm going to put everything on the same side. You get one side equal to 0, so minus 9x. And if I collect these, it's going to be a negative 18 equals 0. We've got two different strategies, choices at this point. I always try to factor if possible. I find it a little bit more convenient and easier to do. If I don't find factors right away, I'll resort to the quadratic formula. So the nice thing about 2 is it's prime, so the only factors of 2x squared can be 2x and x. I know the signs have to be positive and negative. The factors of 18 that I'm leaning towards are 6 and 3. So if I put a 6 out here, I'll have 12. If I put a 3 in here, I'll have the 3 that I need to subtract. So I'm going to go minus 6. It gives me a negative 12x on the outside. And the inside, I got a positive 3x. If I collect those like terms, we'll have 9x. So I'm going to get rid of those comments there. And that is the correct factorization. So we had minus and plus. I just want to get rid of this line underneath here. Once we have this, now we can go ahead and use our zero factor theorem. When we have two numbers that are multiplied together to give us 0, one of these two numbers, either 2x plus 3 has to equal 0, or our x minus 6 equals 0. And we've been doing quite a few of these problems, so by now you can figure out what's the related 0 for this factor, and that is when x is equal to a negative 3 halves, and what's the related 0 for this one, and that is when x equals 6. So our two possible solutions on this are negative 3 halves and positive 6. What we want to do is put those back in and make sure they work. So I'm coming back up in here. I prefer to put them in the factored form. I got to make sure I got the answers right here. Negative 3 halves and 6. So I'm going to try the negative 3 halves and the positive 6. I'm not going to spend a whole lot of time on the positive 6 because I can tell already, I know that I can never divide by 0, and if I put in a positive 6 either in there or in here, that's going to be undefined. So the 6 is going to get tossed out right away. And now the rest of this we could plug in and we can check our negative 3 halves. So I got to take 2 times a negative 3 halves all over. We've got a negative 3 halves plus 3. And we got plus 3 over. Then we got a negative 3 halves minus 6. And I want to see if that's going to equal. And I'm running a little bit out of board space here, so I'm going to have to wrap around here, so I'm going to get rid of it. And maybe I'll just get rid of this and slide that whole thing over. Okay, now is that equal to? And then I lost my factored version of it now, so now it's 27 over, and I believe it was an x plus 3. So our x plus 3 is going to be negative 3 halves plus 3 times, and then our other factor was negative 3 halves minus 6. So will we get the same result? So negative 3 halves times 2, the 2's will cancel, so it's nothing more than negative 3 on the top. And negative 3 halves plus 3, put it over 2, that is a negative 3 halves plus 6 halves. And negative 3 plus 6, that's a 6, so that is still just 3 halves, only it's a positive 3 halves. This one's going to be plus 3 all over, it's a negative 3 halves minus 6, we'll put this over 2 to get a common denominator halves. That's going to make it 12 halves. So it's a negative 3 minus 12 is a negative 15 halves. And then we want to make sure that that's equal to 27 all over. And these should be identical to what we just did over here. It should be a 3 halves times a negative 15 halves. Okay, so we have these complex fractions that we were dealing with at this point. So what I'm going to do is I'm going to say this is really a negative 3 divided by 3 halves. So divided by 3 halves is the same thing as multiplying by 2/3. So I got that. Plus, I've got a positive 3. Only this positive 3 is being divided by a negative 15 halves. So that'd be multiplying by negative 2/15. And that's going to equal, and then we got a 27 all over. And now I can write it as negative 45 all over 4, which again, that's a complex fraction. We'll flip and multiply on it as well. Good things are happening over here. The 3's are going to reduce, so it's a negative 2 plus. Over here, the 3 and the 15 have a common factor, so that's going to be 1 and 5, so plus a negative 2/5. And I want to see if that's the same as over here. We have 27 divided by negative 45, 4, so we're going to take it times 4 over a negative 45. So we can reduce 45 and 27 have a common factor of 3, so that's going to be 9 and 15. So what do we have? We have 9 times 4, which is 36 over, oh, that's a negative, I got to be careful. So we have a 36 over 15 negative. 36 and 15 still have a common factor. I should have noticed that, and then 15 and the 9 would have been a little bit easier, but I can reduce a common factor of 3 out of those. They're both divisible by 3, so it's going to be negative 12 over 5. Okay, so we want to add these together. So in order to add these two together, I get a common denominator of 5, so I got to multiply the top times 5, it's a negative 10. That's a negative 12 fifths. So I can verify that the solution does work, so therefore our solution set, and the other day I talked about creating your solution set, is when x is equal to negative 3 halves. And this just indicates to me that you've gone through the process of checking your work. So like I said, these involve a little bit more work. The concept is still the same. We'll practice it on another problem here in just a moment. Okay, I'm going to continue on then with 7b. The first thing I want to do is make sure that we get it completely factored. So in 7b I got a negative 12 over. On the bottom I'm going to factor out that monomial of x, and it's going to be x plus 6. And then it equals, we've got 2 over. x plus 6, and then plus x minus 2 all over x. And here's where I want to emphasize that whenever you see a fraction bar is a grouping symbol. So this is a factor of x plus 6, this is a factor of x, this one has a factor of x times x plus 6. So when we start deciphering and figuring out our least common denominator, or least common multiple, could actually write it in correct order, least common denominator, we want to make sure that the factor of x is represented in our least common denominator. We want to make sure our factor of x plus 6 is represented in our least common denominator. And this one doesn't have to contribute anything because x and x plus 6 are already shown in our least common denominator. So really what we're doing is we're multiplying both sides of this equation times x plus 6 times x. So x times x plus 6 times, and over here we got negative 12 over x times x plus 6 equals, now I want to take this entire right side, so I'm going to put it in parentheses, or grouping symbols, 2 all over x plus 6 plus x minus 2 all over x. We want to take that times our least common denominator, which is x times x plus 6. So when we distribute, on the right side we have to distribute, on the left side it's just multiplication. This is all over 1. We're multiplying, but we're not really multiplying over addition or subtraction, so we can reduce the common factors of x plus 6 and x. We're left with a negative 12 on the left side. On the right side, when we distribute, the x plus 6 is going to cancel the first time, so it's going to be 2 times x. When we distribute the second time, what we're going to have is the x's reduce, and then we'll have an x minus 2, so it's plus, an x minus 2 times an x plus 6. Okay, so we've gotten rid of our fractions. That's one of our goals. I'm going to leave the negative 12 over there. I'm going to do one more group of distributing. So plus, we'll take our binomial times binomial. We'll get an x squared. We have a minus or plus 6x. On the outside, on the inside, we've got a minus 2x. So that's going to give us a plus 4x. And on the outside, we're going to have a negative 12. We're going to collect our like terms. So when we collect our like terms on this one, the negative 12, when I add it over here, they should reduce. So adding 12 to both sides, we get 0 equals. I'm going to put it in standard form, x squared. Then we're going to have a 2x and a 4x is 6x. So we have x squared plus 6x. Next thing I'm going to do is I'm going to use the factoring strategy. So 0 equals, I'm going to factor out the least common multiple of x, or taking out our monomial factor. We're left with x plus 6. So it appears our related zeros to this equation is when x is equal to 0 or a negative 6. So we need to go back and we need to test these and make sure that they're going to work inside of our rational equation. So 0 and negative 6. If we go back into this factored form, that's what I like to look at. In the factored form, it looks like both of these are bad candidates, because if we put in a 0 or a negative 6, we can't multiply by 0 because that'll create a denominator of 0, so we have to disregard that solution. If we put in a negative 6, it will cause this factor to be equal to 0, and then division by 0 is undefined, so we have to disregard that one. Both of the solutions that we thought were correct can't be used because they create an undefined equation. So this set is the empty set, so our solution set is just an empty set. There's another way that we could write this. If you want to do it, you can write it as the null set. That is appropriate as well. So imperative that you check your solutions to these rational equations so that you don't get misleading results and give me solutions that aren't going to work.